Okay, so we were discussing branching pipes and we discussed how to proceed to solve case 2. Clear? We discussed that if case 2 is given, what is case 2? We saw that in case 2, the elevation for the two reservoir, the surface elevation for the two reservoir is given, and discharge for the third will be given. This is case 2. Clear? And it will be required to calculate elevation of the second reservoir. Clear? So now in this case, how we proceed to solve the problem? So we have to assume the value of EP because we don't know the exact location of EP. Then in that case, we can calculate H1 and H3 using these relationships that we developed earlier. And we can calculate Q1 and Q3 assuming turbulent flow using this equation. Then we have to apply the continuity equation depending on the two cases that we discussed. And we will continue with this EP value unless and until the continuity is satisfied. So as I said that it is a trial and error procedure. So you can calculate V2, Q2 is given. Then we can calculate R2 and F2, Reynolds number and friction factor, and we can calculate H2. And then for the given case, we can calculate E2. So as I said that since it is a trial and error procedure, so minimum we should have 2 trials in order to use this diagram to calculate the correct value of P, which will give us the net inflows, or you should say the net flows, means inflows minus outflows equal to 0. Because in that case continuity will be satisfied. So you can see here this P value for which summation of Q is equal to 0. This is the P value that we want to find. This P value we would like to find. So that's why we are doing the trials, but then we can use this diagram to use interpolation to calculate the correct value of P so that the results can converge. Otherwise we will run for different trials. So the required condition would be that summation of flows at J should be equal to 0. Now let us take a problem. This is problem 8.85 from your textbook. Clear? So in the figure, suppose that pipe 1 is 900 millimeter smooth concrete, 1500 meter long. So now the pipe material is known that it is smooth concrete. The diameter and lengths are given. Pipe 2 is 600 millimeter cast iron. Clear? And it is 900 meter long. Pipe 3 is 500 millimeter cast iron and 400 meter long. So the lengths and diameters and the pipe material, that these are given for the 3 pipes. The surface elevations of reservoir A and C are 60 meter and 30 meter respectively, and the discharge through pipe 2 is 0.3 cubic meter per second of water. into reservoir B. So now you can see this Q2 is given. What is given? E1 is given and E3 is given and discharge for the third is given. And it is given that the flow is into reservoir B. Clear? Find the surface elevation of reservoir B. So it means that we have to calculate E2. This we have to calculate. The water temperature is 15 degree Celsius. So the temperature of water is given, which is 15 degrees Celsius or centigrade. Now, first you have to determine. So far we have studied two cases, case 1 and case 2. So this is case 2 problem. Clear? Now in this case, for table A1 in the book, concrete value for that, the absolute roughness you will take, and for the cast iron, the absolute roughness that you will take these values from table 8.1. Now the water temperature is given. So for 15 degree Celsius or centigrade, table A1 in the appendix of the book, end of the book in the appendix, you can read kinematic viscosity. Now this is the given data. Pipe 1 is concrete, while pipe 2 and 3 they are cast iron. These lengths are given for the 3 pipes. The diameters are given. Now we can calculate E by D. So E is the absolute roughness that you take from table 8.1. Now what is given? E1 is given. This is E1. So this is given. And E3 is given. And Q2 is given. This is Q2. So you can see that the elevation of the water surface in the two reservoirs is given and the discharge for the third is given. So this is case 2. Clear? This is case 2. So now how to proceed to solve this problem? We have to calculate Q1, Q3 and E2. So as I discussed, to solve this problem, first we determine that this is case 2 problem. What we have to do, as I already discussed, that it is a trial and error procedure. We find the elevation of P by trial and error. So we have to assume the value of EP. So EP elevation, it lies between 38 and 60 meter. So this is 60 meter E1, which is given as 60 meter. And this is 38 meter E3. So this is given as 38 meter. As I said that this EP must always be between these surface reservoir elevation A and C. But it is above B or below B that we have to find out. But the value of EP is always below reservoir surface elevation A and above E3. Clear? In all the cases that we consider. Clear? So now we have to start from somewhere, but elevation of P we have to consider between these two elevations. So we go for first trial and let us assume EP equal to 50 meter. This is just an assumption as a first try, that let us assume EP equal to 50 meter. Now EP is known, so we can calculate H1 and H3. The procedure I already explained in the previous slide. So now we assume as a first trial EP equal to 50 meter. Now we calculate H1 and H3. Now EP is known, that let's say this is equal to 50 meter. This is now equal to 50 meter. We don't know about E2. This is unknown, but we know about this. So we can use the relationship. E1 is equal to EP plus H1, and then EP is equal to H3 plus E3. So we can calculate H1 and H3. So H1 will be equal to E1 minus EP, and this comes out to be 10 meter. And H3 will be equal to EP minus E3. So this comes out to be 12 meter. Now that we know H1 and H3, we can calculate Q1 and Q3. And how to calculate? We will assume turbulent flows to avoid the trial and error, because F is unknown. The friction factor is not given in the problem. So it means that you have to assume the F value and then trial and error and calculate the F value, and that comes out to be the same as the assume F value. You can see that will be a trial and error within trial and error procedure. So that's why, to avoid that, we are assuming that assume turbulent flows, and now we can eliminate the friction factor by using this equation directly. So you can directly calculate Q1 and Q3. There is no friction factor in this formula, but the assumption is that we have turbulent flow. So after we calculate the correct values, then you have to calculate the Reynolds number, and it should provide us that the flows are turbulent flow. Only then these results will be correct. So this is the assumption that we have to make. So now using this equation, everything is known. This HF represents H1 and H3 to calculate Q1 and Q3. And then you calculate Q1, it comes out to be this, and Q3 is this. So now we calculated Q1 and we calculated Q3. What about Q2? Q2 is given. Q2 is given in the question, that it is 0.3 cubic meter into reservoir B. This is given in the question. Clear? If I go back to the problem statement, here you can see that discharge through pipe 2 is 0.3 cubic meter per second of water into reservoir B. So this is given to us, into reservoir B. So this is given. Clear? Q2 is given, and it is into B. So now we can apply the continuity equation. This is the requirement, that the sum of flows, inflows minus outflows at J must be equal to 0. So for this condition, because Q is into B, so it means that the continuity equation that we have to satisfy is that Q1 should be equal to Q2 plus Q3. This should be satisfied. Now when you put the values, this is Q1, and we have this 0.3 plus 0.817, Q2 plus Q3 equal to 1.17, and this is 1.747. So what it means? It means they are not equal. Clear? They are not equal. So what we get? This is the required condition, that summation of flows should be equal to 0 at the junction point. At this point, sum of inflows should be equal to sum of outflows. So inflows minus outflows, we get plus 0.63, and this is not equal to 0. If it is equal to 0, then the solution will stop and we get the final answers. But you can see here that summation of Qj is not equal to 0. So now we go for the second trial. Clear? It means that the value of EP that we assume here, 50 meter, is not correct. So now we have to increase or decrease the value of EP. Should we take this EP value up, or should we take this value of EP down? Because this 50 is not correct. So now you can see here that Q2 is fixed because this is given, and Q3 and Q1 we calculated. So it means that this Q2 plus Q3 is smaller than Q1. So it means that we want to decrease Q1 and we want to increase Q3 so that we can bring the left hand side equal to the right hand side. So for this, what we have to do is that we have to move the P up. It means that what we have to do, what we should do, that this will not be correct. We have to move the P up because we want to reduce the value of Q1 and increase the value of Q3 so that left hand side becomes equal to the right hand side. So now in the next trial, we assume EP equal to 55 meter. This is now the second trial. So now EP is known. Again, we can calculate H1 and H3 using the previous slide equations. We can calculate H1. This is now 5 meter, and H3. This is now equal to 17 meter. Now we can calculate Q1 and Q3 assuming turbulent flow conditions. So Q1 comes out to be 1.231 cubic meter per second, and Q3 is 0.974 cubic meter per second. Now Q2 is given. Clear? Q2 is given. So we can apply this continuity equation, and Q1 is 1.231, Q2 is given, and this Q3. So you can see that when we calculate Q2 plus Q3, so again it is not equal. If left hand side equal to the right hand side, then this 55 meter will be correct. Clear? But again, now what is the situation? That summation of flows, inflows minus outflows, that comes out to be minus 0.043, not equal to 0. So now in this case we get negative answer. So it means that you see here the outflows, they are more as compared to the inflows. This is the inflow to the junction point, and these are the outflows. So the outflows are more as compared to the inflows. That's why you get the negative sign. Inflows minus outflows. So again, it is not equal to 0. Smaller value than before, but still not equal to 0. So now what we have to do, we have to move P down. Clear? Because now we want to increase little Q1 and decrease little Q3 so that the right hand side equal to the left hand side. This equation we want to satisfy. We will continue with trial and error unless and until this equation is satisfied. This is our goal. So now that we have done 2 trials, Now we will move up and down, and continue with trials to find the correct value of EP. But as I said before, that we can use this diagram to simplify our solution. So in this case, we use interpolation to get the value of EP. So how we get this value? With reference to this diagram, this EP equal to 54.68. This is this value here. This P value here equal to 54.68. Because at this value, what we get, summation of Q equal to 0. This is how we do by interpolation. And using this equation, we get this value here. By interpolation, using this equation, and this is what you get. So this is the previous value, 0.630, from where it comes. Before I show you how this value comes, this is 0.630, clear? This is the value comes for the first trial. And then this is the value comes for the second trial, clear? So this is how we have written here. Now, how we get this equation here? How we get this equation? So with reference to this diagram, if I plot this diagram here again, you can see here we have summation of Q's, summation of flows. So we have summation of Q here. So in this direction, what we have, the positive values. So we have plus here, and then in this direction we have minus, positive and negative. Clear? So now what we did is that this is elevation P. You can see here this vertical line represents elevation P here. So this is P here. Clear? Now in this case, what you see here, that we come up with the value here when the first we assume, clear, for 55. Clear? First we assume the value of 50. So the value of 50 that we assume, clear, let's say 50 we assume, and for that value we get the value of plus. For that value, what was the value? 0.630. So here for this plus 50 we get here plus value. This is negative, clear? So in this case, just assume this here. So for 50 that we assume in the first, we get 0.630. We get 0.630. Clear? Plus. And then we move to 55. So this is 55. Clear? This is 55 here. Let me take this value a bit up. So we get this value as 55 here. So for this 55 meter, what we get? We get minus 0.043. So minus here in the negative zone, in here in the negative zone. Clear? So for this case, we get this value here. This value here. And what is this value? 0.043. This is 0.43. So now what we do is that I will join these 2 points here. You can see here, one is this point here and one is this point here. So this point here I join. Now this is point here. At this value we have P. Clear? At this point here, for which summation of Q is 0. This point P here, for which summation of Q is 0. You can see here. So here we have summation of Q equal to 0. This we would like to find because it will satisfy the continuity equation. So now if I assume this to be a straight line, so you can see here I join this point here and extend this and make a triangle. Clear? And then from this P here I also extend and come here. So now you can see by similar triangles, as you use this concept here, as you use this concept of similar triangles to calculate the unknown value, you might have used this before. So what we can see here now, look here, 55 minus elevation of P. So this is 55 minus elevation of P. It means it is this distance here. This distance here is here, 55 minus elevation of P. And then we have divided by 55 minus 50. So 55 minus 50 is this distance here, this distance. This is equal to 0.043. What is 0.043? This distance. This is 0.043. Divide by 0.043 plus 0.630. It is this distance from here to here. You add these two, this is what we get from here to here. So this is how we do interpolation. Similar triangles. 55 minus elevation of P, this is 55 minus elevation of P, divided by 55 minus 50. So this is 55 minus 50 equal to 0.043, this distance, 0.043, divided by this distance here. So you can see that we compare similar triangles and we get the value of EP is given as 54.68 meter. So this is how we use this figure to help us. You can see. So now we have elevation of P. You can again find H1 and H3. Clear? This is in the third trial, as we did in the first and second trial. So now H1 comes out to be 5.32 meter and H3 comes out to be 16.68 meter. Now we calculate Q1 and Q3. Again, H1 is calculated and H3 is calculated. So we calculate Q1 and Q3 assuming turbulent flows. Remember, assuming turbulent flows. So Q1 comes out to be this and Q3 comes out to be 0.97 cubic meter per second. Now Q2 is given. We again apply this continuity equation. So you can see here that 1.24, this is Q1, this is Q2, and this is Q3. So when you add now 1.27 left hand side minus 1.27 right hand side, they are the same. So now summation of Qj is equal to 0, means the inflows minus the outflows is 0. So this is the solution. This is the solution. Clear? So now we get the correct values of Q1, Q2 and Q3. Now that we calculated Q1, we can calculate V1. And we can calculate V3 as we already calculated Q3. Clear? And then we calculate R1. And this is 1.577 into 10 power 6. So we have turbulent flow. And we calculate R3. And it comes out to be 2.17 into 10 power 6. So from our values, 4 flows are turbulent. And we assume while calculating Q1 and Q3 that the flows to be turbulent. So it means that assumption of turbulent flows is correct. So now next we calculate V2 because Q2 is given. This Q2 is given. So V2 comes out to be this much. Again you calculate R2 and R2 is this much. So now you can use R2 or you can use E by D also to calculate the friction factor. Clear? Using Moody's chart. Or we can use Haaland equation to calculate value of F. Because this R2 you calculated, so this R you will put here. This is the R value. And this E by D for pipe 2 you can calculate. And now we calculate the value of F2, the friction factor. So now this friction factor we can put in here to calculate H2. And then we can calculate E2. This will be equal to EP minus H2 equal to 53.22 meter. So this is what was required to calculate E2. So now we discuss case 2. Another case that is discussed in our textbook, that is case 3. In case 3, find the flow in each pipe. What we have to do? We have to now calculate the discharge in the 3 pipes. Given surface elevation of all the 3 reservoirs and all the pipe data. So now we have to calculate the flow rates. What is Q1, what is Q2, and what is Q3. And E1 will be given, E2 will be given, and E3 will be given. So this is case 3 now. Now we are given E1, we are given E2, we are given E3, and all the pipe length and diameters are given, and it is required to calculate Q1, Q2, and Q3. Now we have to calculate the discharges in all the 3 pipes. So this is the classic 3 reservoir problem. It differs from the other 2 cases in that it is not immediately evident whether the flow is into or out of reservoir B, because we don't know the position of EP. This is unknown. So since EP is above or below, we don't know. That's why we don't know that Q2 is into or out of reservoir B. The cases that we discuss, it is always from out of reservoir A and into reservoir C. But about B, either into reservoir B or out of B will depend on the value of this EP. If EP is above or more than E2, flow is into reservoir B. If EP is less than E2, flow is out of reservoir B. So that's why this case 3, this in books is known as the classic 3 reservoir problem, and it will be required to calculate the 3 discharges. Now for case 3 situation, then how we proceed to solve this problem. So the first trial will be that we assume EP equal to E2. This will be the first trial. So when EP is equal to E2, it means there is no flow to Q2. To reservoir B, Q2 will be 0. H2 will be 0. This will be the first trial. We will assume because E2 is given. So first we will assume EP equal to E2, in which case Q2 will be 0 and H2 will be 0 because EP is equal to E2. So H2 will be 0. Clear? This will be the first try. Then what we have to do is that we have to calculate H1 and H3. H2 is 0. So we calculate only H1 and H3. And then using these relations that we already developed, because E2 is equal to EP, that's why you can see here and H3, it will be given by this expression, because in the first trial E2 is equal to EP. Now we calculate Q1 and Q3. Again, we assume turbulent flows and we use this equation. We use this equation because this equation helps us to avoid the F value, the friction factor. Otherwise, it will become a trial and error procedure within a trial and error procedure. So it will be very time consuming and the problem solution will become difficult. So that's why to avoid that, we eliminate F using this equation, direct method. But here the assumption is that we have turbulent flow. And in the end, we have to prove that the flows are turbulent, then the results will be valid, as we saw in the solved example previous slide. So you calculate Q1 and Q3 using this equation here, because now H1 and H3 are calculated. H2 is 0 for this assumption, and the check would be that Q1 should be equal to Q3 because Q2 is 0. If it is satisfied, then our solution will stop. But if this is not satisfied, we will go to the next trial. Clear? So if we find out that Q1 is greater than Q3, then this will be the continuity equation, because Q1 is greater than Q3, it means Q1 should be equal to Q2 plus Q3 and flow into reservoir B. That's why Q1 is equal to Q2 plus Q3 here. Look, Q1 out of reservoir equal to Q2 plus Q3 into reservoir. So this would mean that flow is into reservoir B. And if Q1 is less than Q3, clear? Then in that case, Q1 plus Q2, that will be equal to Q3. And this would mean that flow is out of reservoir B. So after this first trial, then from here on, the solution proceeds by adjusting P as for case 2. So after this first trial, for the next set of trials, the solution is essentially same like case 2. Clear? Now let us solve a problem. Now in this case, again we have branching of pipes. So in this case, the pipe length and diameters are given. Length and diameters for the pipes, 3 pipes are given, and the pipe material is given. Welded steel pipe. The surface elevations of the 3 reservoirs are given. Clear? So the datum is here. Rather than here, you see that E3 is 0. So it means that for this case, this is our datum. This is our datum. Clear? This is our datum. Why? Because E3 is 0. Here it is given 0 meter. So for this problem, the datum passes through the surface of the reservoir in C. The water temperature is given 15 degree Celsius or centigrade. Find the flow in all pipes. So now from table 8.1, the absolute roughness for the 3 pipes, now they are welded steel pipes. You can pick this value. And from table A1, for water at 15 degrees Celsius, this is the kinematic viscosity value. Clear? And this is the given data. So you can calculate E by D easily. This is the diameter and E is here. And now the elevations for the 3 reservoirs is given. Clear? And it is required to calculate Q1, Q2 and Q3. So this is case 3 problem. What was case 3? That E1 is given, E2 is given, E3 is given, and it is required to calculate Q1. So now we have to calculate this Q1, we have to calculate this Q2, and we have to calculate this Q3. So now we have to solve by trial and error procedure. For the first trial, we assume EP equal to E2. This will be the first trial. So in that case, Q2 will be equal to 0 and H2 will be equal to 0. No flow, so no head losses. So now find H1 and H3. H1 you can calculate for this case here. It comes out to be 14 meter. And similarly, we calculate H3. It comes out to be 22 meter. Now that we know H1 and H3, we can calculate Q1 and Q3 using this equation. We eliminate F because friction factor is not given in the question. So to eliminate a trial and error for F, we directly use this equation here. Just you put H1 and H3 in here and in here the rest length and diameter. We can calculate Q1 and Q3. So Q1 comes out to be this much and Q3 comes out to be this. Now we check because Q2 is 0 as we assume EP equal to E2. So now we apply a check that Q1 should be equal to Q3 because Q2 is 0. What we calculated Q1, this comes out to be 1.088 and Q3 comes out to be 0.4. So this is not the same. Clear? So it means summation of Q that is not equal to 0. If summation of Q was equal to 0, then these are the correct values. We will say Q1 is equal to Q3 correct value and Q2 is equal to 0. But since this is not the case, because summation of j, the required condition, that should be 0, is not equal to 0. So now we proceed for the next try. Now what we have to do is that you can see Q1 we need to reduce and Q3 we need to increase. So for this what we have to do, P must be raised. We have to increase the value of P. Then water will flow into reservoir B. Because now we want to raise P. So now if we make EP greater than E2, if we make EP greater than E2, now we find out after first trial that we need to increase the value of EP. So if we raise EP, then it means this is the case, what we get. EP greater than this E2. So then it means flow will occur into reservoir B. Now for the second trial, as Q1 is greater than Q3, assume EP greater than E2. So now E2 is given and E1 is given. So EP we assume 29 meter midway between elevation of reservoir A and elevation of reservoir B. This will be our second trial. So now we assume this 29 meter midway between A and B because we don't know the correct location. So the next trial we will assume the middle value. This is just an assumption. So now we know EP value, we can calculate, and this will be the continuity equation because we say flow will occur into B. So in that case, we have to satisfy Q1 equal to Q2 plus Q3. So now that we know EP value, we can calculate H1 as we have done so far. So we can calculate this. And similarly, we can calculate H2. It will be given by this. And we can calculate H3. Because E1, E2, and E3 are given. E1 is given, E2 is given, and E3 is given. E3, 0, given. So for this 29 meter EP, we can calculate H1, H2, and H3. So now that we can calculate these, we can calculate Q1, Q2, and Q3. Clear? Using this equation here that I showed here, this equation. We can apply this equation to calculate the three discharges. H1 here we put to calculate Q1, H2 we put here and the rest of the data to calculate Q2, and H3 put here the rest of the data for pipe 3 to calculate Q3. So that we apply here and we calculate Q1, Q2 and Q3. And now this equation we have to satisfy. So Q1 should be equal to Q2 plus Q3. So when we put Q1 here, this is equal to Q2 you put here, and Q3 here you put. So you can see here that this is not equal to this 1.105 and this is 0.759. Clear? So we get some net summation of n flows, that is minus 0.346, not equal to 0. So what we do, P is too high. Clear? We need to decrease the value of P. This P value is too high. We need to decrease the value of P. So again, now we are done with two trials. Now we can use this figure for interpolation. So that to reduce, the purpose of this step is to reduce the number of trials. Otherwise, without this help or interpolation, the number of trials will increase. So after two trials, we can use this figure as I already explained in the problem before. we can use this interpolation. The same concept as I already explained. And now from this interpolation, we get the value of 26.6 meter. So now this is the new EP value. Again, we calculate H1 like here in second trial. We calculate H2 and we calculate H3. Clear? So now for this H1, H2 and H3, again we calculate Q1, Q2 and Q3. So Q1 comes out to be this much, Q2 is this, and Q3 is this. Now we apply the continuity equation. Clear? So the continuity equation is that Q1 should be equal to Q2 plus Q3. So when we add, you can see Q1 is 0.885 and Q2 plus Q3. This comes out to be 0.962. So again, it is not same. Clear? Although it is close, you can see here 0.885, it is closer than before. And this is 0.96. But still, if you want to increase the accuracy of your results, this is, now it is 0.077. Again, not equal to 0. Although the difference is small, but if we want to increase the accuracy, we go for another try. Clear? So we can try again. Again, instead of interpolation, we can use extrapolation. And the same process as I already explained, we get the value of P as 25.9 meter now. And now for this EP equal to 25.9 meter, we go for the fourth trial because we want to increase the accuracy of our results. So now assume for this EP 25.9 meter here. And again calculate H1, H2 and H3. For this again we calculate Q1, Q2 and Q3. So these are the values for the discharges. Now this continuity equation has to be satisfied if these values are correct. So you can see that Q1 is 0.919 and if we add Q2 plus Q3 comes out to be 0.913. So this is now close enough. 0.919 and 0.913. Now we calculate V1. Clear? It is equal to Q1 by A1. Discharge is known. So this will give us V1. And we can calculate R1. And we calculate R1 and we have turbulent flow. Because these discharges that we calculate from equation, there we assume the flows to be turbulent flows. Similarly, we go for V2. This will be here, Q2 here. You can calculate V2, area A2 is known. We calculate R2 and it is given by this value. Similarly for V3, this Q3 here, we use to calculate V3. And then we calculate R3. So you can see that all the three flows are turbulent as assumed, because the equation that we use to calculate this Q1, Q2 and Q3, it says that the flows should be turbulent flows. So in the end we have to verify that yes, the flows are turbulent flows. Then this Q1, Q2 and Q3 are correct values. If this assumption is not valid, then this will not be the correct values of Q1, Q2 and Q3. So now we have found out that all the three flows are turbulent. Here you can see the Reynolds number for turbulent flows as we assumed. So now we get the correct values of Q1, Q2 and Q3. This is what was required to calculate the discharge Q1, Q2 and Q3. So these are the correct values for the discharges. So this is how we proceed to solve case 3. Now next we have some empirical equations available to us that we can use to solve the pipe flow problems. So the first one, that is the Hazen-Williams formula. So in the British gravitational units, these are empirical equations. So we get them from the data. So that's why we directly write down the equations. It is given by this expression in the British gravitational units. And in SI units, this is the formula to calculate the velocity V of flow in the pipe. So this Hazen-Williams formula, why we use these empirical equations? We use them to our benefit, because earlier when we tried to solve the single pipe flow problems, we realized that there is a friction factor involved. And since mostly we encounter turbulent flows in nature, so for that we are using the Colebrook equation. And in the Colebrook equation, F was present on both sides. And essentially to calculate F, you do a trial and error. And then if you have, let's say, 500 pipes in the problem, 500 times you have to do the trial and error. So it was very time consuming. So that is why this Hazen-Williams formula was developed to avoid the trial and error procedure that is given by F. You can see here, there is no F. There is no friction factor. So later on, we have the Moody's diagram or Haaland equation that simplify, but it happens later. In the beginning, when we only work with the Colebrook equation, it was trial and error to calculate the F. So that's why scientists, engineers, they come up with these empirical equations to simplify the procedure. Clear? So one of them was the Hazen-Williams formula. So they conducted a lot of research on pipe flows, and then they developed tables to calculate for this coefficient here. You see, RH is the hydraulic radius. So we already know how to calculate the hydraulic radius. S is the slope, HL by L. Clear? So the head loss divided by L, this is your S, the energy gradient. And velocity we want to calculate. So this coefficient, which is known as the Hazen-Williams coefficient, what essentially they did is that they developed tables for this and published in the form of booklet for different conditions. Clear? And we can pick the C values from those tables that we can use here and easily calculate the velocity, multiply by the area, easily calculate the discharge. So this way, the F, the friction factor, was eliminated. Clear? This formula is applicable only to the flow of water in pipes larger than 2 inch and at velocities less than 3 meters per second. But it is widely used in the waterworks industry, water supply industry, waterworks industry. They are widely used this Hazen-Williams formula. Clear? So the advantage, as I explained, of this formula is that, or the pipe friction formula, the Darcy-Weisbach formula, is that roughness coefficient CHW is not a function of the Reynolds number and trial solutions are eliminated. Clear? Because we saw that F, the friction factor, and the pipe friction formula or the Darcy-Weisbach formula, that was a function of Reynolds number. So that's why we face the trial and error solutions. One advantage of this Hazen-Williams formula was that we avoid the trial and error solutions. And these coefficients were developed for different pipes. Clear? Very smooth straight pipe, new riveted steel pipe, old and tuberculated pipe. These are given in your textbook. but they developed table for different pipes from where we can pick the value of this C, and that we can put here to calculate the velocity, and we are able to calculate the discharge, and we eliminate the trial and error solutions. So that's why in the waterworks industry, AWA, if you have heard the term AWA, American Waterworks Association, so they extensively use this Hazen-Williams formula for analysis of pipe networks. The second formula is that of Manning formula. So the Manning's formula in the British gravitational units, it is given by this. RHV is the velocity, RH is the hydraulic radius, S is the slope of the energy line. And in the British gravitational system, it is given by this equation. In SI units, it is given by this expression. So this formula, which was developed by Manning, an Irish engineer, so this formula is known as the Manning's formula. This formula is extensively used in open channel flow. Next semester, you will study the course of hydraulics. You will see that Manning's formula will be extensively used. But this Manning formula is also for the pipe flow. Clear? This is also for the pipe flow. We use the Manning formula. And in this formula, N is the roughness coefficient. And again, tables are developed for the roughness coefficient N. So the Manning formula applies to about the same flow ranges as does the Hazen-Williams formula. You can see, you will find tables in the books. They give the value of N for the different nature of surfaces where the flow occurs. Clear? So we can use directly N from here that you put here, and we can avoid the trial and error procedures because of the friction factor. So these two equations, these are discussed in our textbook that we can use to solve the pipe flow problems. Clear? And it avoids the use of the friction factor. Clear? Now, if we have a pipeline with a pump, let's say we have two reservoirs, and as I said, that pump, it adds the energy to the flow of water. With the help of pump, we lift the water and then it is discharged to another reservoir here. So if pump lifts a fluid from one reservoir to another as shown, not only does it do work in lifting the fluid height delta Z, but also it has to overcome the friction loss, including the minor losses in suction and discharge piping. So the friction head loss is equivalent to some added lift, so that the effect is the same as the pump lifted the fluid the height this much. What we say here is that you want to lift the water from this level to this level here. Clear? By the difference of the two is delta Z. And let's say this is known to us that, okay, you want to lift the water by, let's say, 100 feet. Clear? So in order to lift the water, you have to add the energy. And when we add the energy, we have to provide the pump. So the pump will lift the water. But we say that pump should not only lift the water by delta Z, because the water flows in this pipe, suction pipe here. This is suction pipe and this is the discharge pipe. So it means that the water flows in this pipe BC and DE. There will be friction losses and there will be minor losses. So it means that the pump should lift the water by more than delta Z to overcome the losses also. Otherwise, this delta Z will not be achieved. I already explained this in my previous lectures. So it says that the pump, the effect is that the pump lift the fluid by the height delta Z plus summation of HL. And this HL is sum of the major and minor losses. And then the power delivered by the to the fluid by the pump will be gamma Q, into this, because you already studied previously that power of the fluid that is equal to gamma Q into H. This is the power. So gamma Q into H, this is now the total head. This is the power the pump has to deliver to lift the water from A to here. Clear? And it will include the necessary lift, plus it has to overcome all the losses. If we do not include these losses, pump will not be able to lift the water by delta Z, because some of the head will be lost as energy, as we are already studying. So this power has to be delivered by the pump. But actually the power required by the pump will be greater than this. Why greater than this? Because the pump is not 100% efficient. As we already studied that none of the machine is 100% efficient. If pump is 100% efficient, then this is the power required for the pump to deliver. But since none of the machine is 100% efficient, it has efficiency 80%, 90%, 95%. So then in that case, the power required will be greater than this value, depending upon the efficiency of the pump. Clear? So remember, the pump head that is required will be this. Clear? Comparing the required head and the losses. But then because of efficiency, it's not 100% efficient. So again, the head will be required more than this, depending on the efficiency of that. And this we will study when we study the pumps chapter later on in the course. Similarly, in this case, if pump discharges a stream through a nozzle, not only has the liquid been lifted height delta Z, but also it has received kinetic energy. You can see here, if in the end we have a nozzle, so the liquid has received kinetic energy also. Clear? Because of this nozzle. Purpose of nozzle is to convert pressure energy into velocity, kinetic energy, velocity head. Clear? So then in that case, the total pumping head will be delta Z plus V square by 2G plus the head losses. So in any case, the total pumping head may be determined by writing the energy equation between the point upstream of the pump and any downstream point. So it says that this is the pump. You want to calculate the total pumping head that is required. Just you consider any point upstream and any point downstream and write the energy equation. So you will get the HP required to be supplied by the pump. Clear? So we will study this in detail in pumps chapter. And instead of pump, if we have a turbine, so as you already know, the turbine is a machine that is employed for converting energy of flow into mechanical work. So it means that pump aids the energy, turbine takes away the energy from the flowing fluid. Clear? So the inflowing from upper tank to the lower fluid loses potential energy delta Z, because now the fluid is coming from this upper here to this lower layer here. So what is happening that the fluid loses this delta Z. But now the turbine is here. This is the turbine. Clear? So the power that reaches the turbine is the initial power minus the friction losses. So what we can write down here, the power that is available to the turbine, that will be gamma Q into delta Z minus HL. Why HL? Because the fluid flows from this point here to this point. There are losses here. In this length, there will be losses here. So it should be gamma Q. If there are no losses, then it will be gamma Q into delta Z. This will be the power available to the turbine here. But since the liquid flows from here to just before the turbine, that's why we have these head losses. When it reaches here, you can see the piezometer here, it shows here. So this is the losses. So that's why the head available is not this one, but it is delta Z minus the head losses. This is the power available. And the power that turbine delivers is less than this power. This is the power available to the turbine. And then it converts this fluid energy into mechanical energy. And later on that mechanical energy is converted into electrical energy. So the pump, this is available to the turbine. This much head power is available to the turbine. But the power that turbine will deliver, that will be less than this because of the losses in the turbine. As I said, for the pump, no machine is 100% efficient. So that's why this much is available power, but the turbine, what? It will rotate the shaft, clear, the shaft of a generator, and the generator will convert mechanical energy into electrical energy. So the power available is this much, but the turbine will deliver power less than this to the shaft of the generator, because turbine here, the turbine, it will deliver the power less than this because it's not 100% efficient, because it has hydraulic and mechanical losses. So the head under which the turbine operates is this. This is the head available to the turbine from here. Clear? So we will discuss pumps and turbines in detail in the coming chapters. But here, if in a pipeline pumps and turbines are connected, this is how we use these equations to solve the pipe flow problems. Clear?